Thank you and welcome to this presentation. My name is Gianluca Gerard. I'm the Chief Technology Officer of Sorintec. Sorintec is the business unit which is specialized and focused on data, big data and machine learning in particular. So, as part of my activity, I'm also completing a PhD at the University of Pavia in deep learning, and this is the reason I'm going to bother you on this topic. I hope it will be interesting. It's mostly a state-of-the-art overview. It's a field which is changing so fast that I think it's really important to know what is available right now, because it's completely different from what was available just a couple of years ago when I started in this field. So for those of you who know the Game of Thrones, why this title? Well, because deep learning, as maybe you will appreciate, is a very stupid technology, to be honest. It's nothing exceptionally clever or anything, but the results have been, especially recently, outstanding. And there is a thought that maybe it could be a solution to many more problems. So this is the reason of the title here. Okay, so let's dive straight into it. For those of you who do not know what deep learning is, this is a very high-level overview. Well, basically, deep learning is part of the broader area of artificial intelligence. What is artificial intelligence? It's difficult to define, but it is a discipline which tries to basically achieve with computers the same results that we as a human are able to achieve. So it's trying to replicate natural intelligence. As part of in the field of artificial intelligence, there is machine learning. Machine learning is basically everything which relates to algorithms, where basically these algorithms are learn from the data how to complete certain tasks. So it's different from traditional programming. In traditional programming, you have a programmer who has basically a set of rules, and the programmer is just translating this set of rules into code, and eventually the program will be able to complete the task. Machine learning is used when instead a programmer does not have a set of rules, nobody is able to write down this set of rules, like computer vision. I mean, recognizing an object, you do not have a set of rules to recognize an object. So in that case, you use machine learning. You present and the algorithm learns how to recognize an object. Deep learning is a subfield of machine learning, and it is the subfield which is exactly concerned with trying to replicate the way our brain works, so to speak. This is a famous, for those of you who are active in this field, overview of what are the human competencies. And basically, as time goes by, we see that the landscape, this world, is submerged with water, and everywhere where you see water, basically, is something which has been already achieved by computers. So as time goes by, obviously, the level of the water is rising. And it will be just probably a matter of time until other skills which are now a preserve of human intelligence will be conquered by computers. And the most recent achievements have been Go, playing the game of Go. Just a few years ago, it was thought that computers could not beat a human in playing Go, and just a few years ago, since a few years ago, this is no longer true. Computers are way better than humans at playing this Asian ancient game. All right. So, as I said at the beginning, deep learning are all the algorithms in machine learning which are basically trying to mimic the way the brain works. Well, this is not a new idea. It's an idea which started in the 50s. Even with von Neumann, he was one of the scientists which started thinking about this possibility. And well, in the 50s, the idea of how a neuron works was kind of naive. It's not true, basically, that a neuron really works in this way. But so to speak, neurons are basically input-output processors, which takes their input from a number of connections, which are called dendrites. And it does some form of computation, and then you get an impulse, which is carried by axons. And these axons terminals will connect to other dendrites. So this is a very cartoonish representation of how neurons work. Well, basically in the 50s, this was the idea. And so, mathematically, they thought that it could be possible to represent the way a neuron works in this way, which is very simple representation, but it is the one which is still used today in deep learning. So nothing has changed since the 50s. We just connect more neurons in more clever ways, but each neuron behaves in exactly this way. So basically, you take the input, which are probably coming from other sensors or from other neurons. You basically multiply each input with a weight. And what you do is that you sum all these multiplications together. So what you basically get at this stage is the weighted average of the inputs. You apply a function to this value in order to get a value z, which will be sent to other neurons. Okay, so very, very simple. And the way these neurons are classically connected is this way. This is called an artificial neural network. In particular, this is, for those of you who know a little bit more about this topic, this is a representation of a fully connected neural network. What does it mean, fully connected? Basically, it means that every neuron in each layer, okay, so we have this hidden layer 1 and hidden layer 2 and the final output here. Well, basically each neuron in each layer is connected to every other neuron in the layer before. Okay, so very, very simple. I mean, very, very simple to compute, very, very simple to use. But what is surprising about this architecture is that basically it's been demonstrated that even with this simple architecture, you can approximate every possible function. So the artificial neural network, even in this simple form, is known as the universal approximator. And a more recent discovery has been that if you have more layers, well, basically your representation capabilities are much better. You need less neurons in order to make a good approximation of these functions. An example, if you want to create a neural network which just multiplies n numbers, if you have just one single layer you need 2 to the n neurons to complete these multiplications, but instead, if you have a deep network, you can have or you can use just 4n neurons, which is way, way less. And so basically the representation capabilities of a deep network are much more powerful than the representation capabilities of what is called a shallow network. And this is the reason basically deep networks have changed the game recently. In the 50s, the theory was all there, but the computers were not fast enough basically to have a lot of layers. These days, obviously, we have fast enough computers to be able to use as many layers as you want basically, and so much faster and better networks. Well, this is a demo. You can try it yourself on playground.tensorflow.org. I hope it will play, and this is a demo of a network which is learning this simple function. This is the XOR function. The way it works is very, very simple. We do not tell the algorithm how to compute this simple function. We just present to this function many, many examples, okay? Which means that we provide many, many times, over and over and over, basically, these examples, so the set of inputs and the expected result, and eventually the network will learn how to compute the same function. The way it works is not part of this talk. We do not have time, but basically there are algorithms so that you learn the weights here, the famous weights that we have seen before when we were discussing the neuron. So when we were saying that each neuron is doing just a weighted average of the inputs. Well, basically the trick here is to learn the correct weights. And there are algorithms so that just by presenting the examples, you know and you learn the correct weights to compute any possible function. So from the XOR function to, let's assume, even a network of logical operator function, XOR, and not whatever you want. A neural network will be able eventually to replicate that same function just based on the example. If you want to try more configurations and more architectures as well, then just go on Playground and you will be able to try it. Okay, so this was just a recap, an overview of what we talked about. But as I promised at the beginning, what I want to share with you is, as I said, the state of the art. Well, before starting with the state of the art, let's just see what has been done yesterday, because it was just actually 7 years ago, almost 7 years ago. It was September 30th of 2012 when this guy, Alex Krzyzewskis, basically in Canada, and some of his colleagues, they tried to use a neural network to solve this or to participate in this challenge. The challenge is called ImageNet, and this challenge is about recognizing among 1.2 million images 1,000 categories, 1,000 different objects. Well, basically, before Krzyzewskis tried his neural network, the best team was able to achieve an error rate of 25%. So basically, one image out of 4, they were not able to classify it correctly. In 2012, this guy used his neural network, he was able to achieve 15.3%, which was 10% better than anybody else. It was an incredible achievement, and he was able to do that by training his network for 6 days on 2 consumer standard graphical processing units, the stuff that everybody at that time was using to play video games. So nothing very expensive. Well, after this breakthrough, because it was a breakthrough, everybody switched to neural networks. And the challenge went on for, in total, 7 years, from 2010 to 2017. In 2017, basically, they decided to stop the challenge because there were no further improvement possible. The machines were more accurate than humans in recognizing these objects. So the error rate of a human, of everybody, is higher than what a computer now is able to do. So it was an incredible achievement. Nobody in 2012 believed that that would have been possible, and it would have been possible so soon. In 2012, if you would have asked the most famous AI expert in the world, and you wanted to make him look like a fool, you would have just asked him, okay, now try to distinguish this remote from this microphone. It was not possible. It was simply not possible. Now it's something that everybody can do. And in fact, everybody can study this stuff. You can even try this stuff on your browser. It's surprising. With just a standard browser, as you can see here, we are recognizing frogs, horses, and it was running on my browser when I took the video. Track and track. This is an error. This is correct, airplane. I hope you can see it. I don't know what it is. It's a truck, according to him. A horse, as you can see, is almost perfect. I'm not sure if this is a cat. This is a deer. He's not so sure. It might be a deer or a frog, but it is a deer. It's impressive. It's really impressive because, first of all, it runs on a browser. And what can I say more? It's able to recognize stuff which is just 32 by 32 pixels wide, which sometimes I have doubts how to work. Well, unfortunately, we do not have time to tell you what this stuff is all about. These are the activations of the networks. So basically, we are inside our network, and we are seeing multiple layers of this network. But the concept here is basically that with this kind of stuff, you present an image, so an input, and you get a set of choices and a probability associated to each of those choices. And if you want to learn more, please have a look at this training from Stanford. It's online, it's free for everybody. It's great. It teaches you everything you need to know about these deep learning systems. All right. Now to a real network. So the one which was running in my browser was almost a toy network, very good, but a toy network. This is a good one instead, one which is used in production these days. As you can see, a lot of layers, a lot of connections. Every one of these boxes is not a neuron, it's a set of neurons. So you need, obviously, powerful systems, powerful processors, which are able to operate in parallel in order to run something like that. But this is not even the latest. The version 3 of this network is the latest, are very, very big. But the bigger they are, the better, obviously, the results that they can achieve. So, basically, 2 key points here. As I said, the theory is available in the 50s, 60s. But what really changed the game are through the internet. With the advent of the internet, it was possible to collect huge data sets, because unfortunately, even to this day, need a lot of data. millions of images, and with video games we got graphical processing to run in parallel massive computations. So these are the reasons why today we are here discussing this technology. It was simply not available before. I started using neural networks in my previous career as a physicist in the 90s, and the results were even if you had a parallel processor available with about 64 CPUs, which at that time it was impossible to train that stuff standard that you needed in order to achieve your results. 20 years later, it all changed. And now everybody can run, even on this laptop. I mean, it's very, very easy. It has a graphic processing unit, and you can run it on the laptop. Anyhow, takeaways, big takeaways. If you're interested in applying deep learning in your business, first of all, maybe you do not need now these days millions of data points, but you need high quality data, which means that every data point has to be labeled or classified accurately, either by a human or by another machine, but it has to be accurate. And these days, obviously, the availability of dedicated AI chips, so parallel chips, is becoming more and more common because obviously speed in order to train effectively your data. And that brings us to today. Today we see a lot of investment which is happening right now. Hot Chips 31, which just finished a few months ago. It's a famous conference for everything related to processing unit, and there were a lot of speeches about AI chips. We have just seen the largest wafer scale chip which has ever been built from Cerebras, which is dedicated to networking. Tesla, in each of his machines, is now installing custom chips for computer vision. This board here. Huawei, just a few days ago, basically discussed about this dedicated AI processor, which is roughly 10 times more efficient than the best graphical processing units available on the market. So there is, and we will see a lot more in the coming months and years. So a lot of investment is going into this. Computer vision. Well, I chose to discuss this one, which was published in Nature in 2018. Well, I was in London recently for a conference on medical imaging, because this is what I do at the university, and they were discussing exactly this study, which was unbelievable. Questions later. It was unbelievable because they had in UK a national wide problem. Basically, there were these 3D scanners for your eyes, and these 3D scanners now are commonplace. So you get to an optometrist and you get a 3D scan of your eye for free. Problem was that nobody was able to read this or to understand what the scan was doing. So these optometrists basically were sending to the National Health System in UK a lot of patients telling the National Health System, you have to help this guy because he's going to become blind in just a few months. Problem was that a lot of these guys, they didn't have any illness, and so they basically bogged down the queues of the national health system. And the problem was that if there were some guys that were actually at risk, basically they got delayed. Their screening and the diagnosis got delayed. It meant that these guys basically become really blind because they there were too many people to visit to diagnose which did not have any illness at all. So a big problem, a big problem. The solution they implemented was to use deep learning in order to use these systems, but with an algorithm which has now learned to recognize whether or not you are actually at risk of having that illness which will make you blind or not. And now this algorithm is performing better than the better ophthalmologist in UK. Impressive, really, really impressive results, which was achieved with really standard systems. The problem for them was to collect high quality data. For them, together with Google and the best universities in UK, took almost 2 years to get to the actual data they needed to train these algorithms, and then they succeeded. Well, this is another example of what you can now achieve with computer vision. This is a Tesla. That Tesla chip that we saw before were producing this kind of results. So from the camera, this is obviously the frontal camera. Each car now has 2 frontal cameras and 3 rear cameras, and they are able to connect the one machine seen on the left camera. They can track it also on the other cameras. But this is the kind of basically performances that you can get. And as you can see, it's impressive because basically this machine is able to see basically everything, way better than a human. I mean, it's able to track all the cars, all the pedestrians, everything which is happening in real time. It's really, really impressive. And this is the kind of performances we are now able to achieve with deep learning applied to computer vision. It's pretty standard. We also do that in our business for other reasons, obviously. Computer vision, well, it's becoming more and more affordable. Now we have frameworks like the FastAI framework, which is able with relatively low cost to achieve impressive result, 93% accuracy on ImageNet with just $40. Everybody can afford it. And in just 18 minutes, remember, it was 85% in 6 days. Now it's 8 minutes, 93%. We have more and more investment creating these architectures automatically in order to basically be able to run these computer vision systems on phones in real time with very, very good accuracy. The problem of running all that stuff on a mobile phone is your energy budget, basically. And so this is quite an achievement for that. So the same level of performance now is available on your phone without obviously draining completely the battery. It's not just computer vision. In 2008, we saw in language processing the same incredible results of performance improvement that we saw in 2012. And this is due to basically now we have pre-trained language models, which are very similar to the computer vision pre-trained models that we are now using in computer vision. And so just to give you an idea of what is achievable, well, basically what happened was that there were certain ways to score how good an person was to understand natural language. Well, in just 13 months since 2018, this particular score went from 69 to 88, and humans in that score were able to achieve 87. So this score, this particular way to measure whether or not you have a good understanding of language, was no longer sufficient to discriminate between computers and humans. And now there is a new score in order to continue to be able to continue to track this. This is impressive. Nobody, I mean, the glue score was defined in 2017, and in 2 years they had to change it because nobody was expecting that something like that would have happened in just 13 months. And what are you able to achieve now? Well, you might have heard of it. OpenAI, they in a few months ago, basically they decided not to release this pre-trained language model, which is called GPT-2. They released just a very small version of it. Why they decided not to release the full version? Basically because this full version, when prompted with a sentence, was able to automatically generate a text which was so good that nobody could realize whether it was written from a human or from a computer. So basically there was a risk, and there is still a risk, a very high risk, that someone could flood the internet with fake news, and nobody would be able even now to distinguish those fake news from real news. It was such a high quality, which someone said that it was New York Times quality in written prose. It's unbelievable. And so they decided to release this code in batches, basically. Now they just released a few days ago the large model. They didn't release yet the extra large model. But now you can apply and use this large model. And well, if you have time to read through it, basically this is what was the input, and this is the result. And you can try it. It's unbelievable. So basically, you get a free text, and it all makes sense. It's almost fun to read. It's unbelievable, really. They decided to release it in batches so that someone else will be able to come up with a way to distinguish this text from something which a human would have written. As I said, to avoid fake news, to really completely flood the internet and the web space. What is even more mind-boggling is that if you apply this same model, which is basically just generating text, to other tasks which are related to language processing, like this one, resolution of an ambiguous pronoun, it's even able to solve this kind of stuff, which is very, very difficult. I mean, if you read it, the trophy doesn't fit into the brown suitcase because it is too large. A human readily understands that it relates to trophy, right? But if you change it, the trophy doesn't fit into the brown suitcase because it is too small. Well, in this case, it relates to suitcase. So this pronoun relates either to trophy or to suitcase just based on this adjective here, right? And in the past, it was not possible for a computer. It was not easy to correctly associate it to the correct noun. Now with the GPT-2 model, it is unbelievable. And there are many, many other examples. It can be used, this same model, to automatically generate code for you. So basically, you write a line of code, and it will provide you with a number of suggestions. It was trained basically on Stack Overflow. So from Stack Overflow, and everything makes perfect sense. And I bet any programmer would be much, much faster in programming Python code. It works in a number of languages, probably 12, 15 languages. So impressive, really, really impressive. Well, unfortunately, we don't have much time, but I wanted also to give you an overview of another impressive achievement, which is in game playing through reinforcement learning. Reinforcement learning is basically this. I mean, you teach an agent by providing a reward how to behave. Okay, like these two cats. All right, they learn to play the ding just by providing food when they press that dong. Basically, this is not a new idea, but in 2013, Google DeepMind basically merged reinforcement learning with deep learning. The deep network is used basically to decide what is the next best action, the most probable next best action in order to maximize your expected reward. And the result was, which was kind of a shock for everyone, in 2013, basically this network, just by looking at the pixels of this game, you're nobody as old as me, so you have not played to this game on a real Atari. I did, and basically this algorithm, just from the pixels, is able to learn how to play this game, Breakout, which, by the way, was programmed by Steve Jobs, if you do not know. It was one of his first jobs of Steve Jobs was to program Breakout. Well, now it's not very good, is it? But after a few more training, after 2 hours, it now plays like an expert, as you can see here. And this is just by looking at the pixels, okay? So it's nothing else. It's just looking at the video. That's impressive, really. And it learned It learned to maximize, basically, the score. This is what it was. But something else happens after 4 hours. It no longer plays like an expert. It basically devised a new way to play Breakout that, as you will see in a moment, it decided that the best way to beat the game is this one. You basically create a tunnel, and then the ball will destroy the wall for you. And this is not the first time. I mean, this was the first time we saw this, but then the same technology was applied to the Go game, and which was thought at the time it was not possible for computers to beat humans. Well, it happened in 2016, and now the Go experts, human experts, are studying what the computers are, the moves of the computers, because they are able now to generate new moves which nobody for hundreds of years ever thought about. And instead, computers now have moves of playing which is very, very effective. Well, DeepMind has spent millions and millions on game playing. It's obvious. The interest in game playing is solving actual problems, actual reasoning problems in a simulated environment. It costs a lot, still costs a lot. So in order to develop the StarCraft 2 version of the game playing with the deep reinforcement learning, it cost, only the training cost them $26 million. It's a lot. But it is able now to solve also robotics, as you can see here. The robot with deep reinforcement learning is able to learn how to move the cube to reach this goal. It takes a lot, it locks a time and a lot of...
programming for any one specific task. Here, a robot has learned to rotate a block into any orientation we'd like. Once it succeeds at that, we give it a new goal, and so on. The system runs on a human-like robot hand, and we use reinforcement learning and simulation to teach the robot how to solve problems.
Okay. Let's move on, because in the interest of time, it does not always work well. So, for example, sometimes if you are not very careful how you are choosing your reward function, it might find a solution which is not the correct one, like this one. Basically, it learned to circle in this area in order to collect these turbo coins, It was obviously not the intent. The intent should have been to complete the track in the fastest time. So the reward function is very, very important. Otherwise, you will find out yourself in a situation like that. So it's very difficult to use, but obviously very, very powerful if used correctly. Okay. Now, obviously, there is a lot of investment in trying to move this deeper reinforcement learning into real production from Facebook and from other organizations. But let's move on to what will happen tomorrow. Well, there are still problems. This is the first one I want to tell you about. Learning to learn. What does it mean? Well, basically, even a kid can learn how to recognize an object by just looking at that object once or twice. Well, this is not true for deep learning. So this is an area of research which is currently actively investigated. And this is what we're doing at the university for medical images, because obviously when you are moving to medical, you do not have a lot of examples of a particular illness. And so you want to apply this technique even when you do not have, luckily enough, a lot of examples. So this is one thing which will be solved. I mean, the investment is huge in this area. The progress since I started a couple of years ago has been staggering. So we are not that far from solving this problem. This is an example. Basically, this system is able to recognize these particular birds by just providing him with a single example of that bird and other classes as well, which is really impressive. This was announced just a few months ago. And what to expect next? Well, someone is thinking that probably machine learning and computers, and another technology which has been around for 30 years probably, but now we are seeing real examples of quantum computers. Well, quantum computers are very, very effective for optimization and sampling, which is very, very relevant on machine learning. So probably we will see some cool progress in the next few years from now, probably in the next 5 or 10 years. It will continue if obviously the investment will continue growing, because obviously there are a lot of costs, especially in research. But for the moment, it goes on unabated, I would say. So yeah, we should see some cool new achievements in the next few years. Obviously, I mean, a reminder for everybody that these algorithms are becoming really, really powerful. It's important for everyone, companies, societies, to start thinking ahead of what will change in the next few years. I mean, a lot of jobs obviously will disappear, and we will see AI applied more and more fields, including the military. The militaries are investing billions on stuff. So the wars in the future will probably change due to this technology, and everybody has to change. With that, we don't have a lot of time left. So if anybody has any, go ahead.
Can I ask a question?
Yeah, sure.
Okay, so we have discovered also how machine learns from the image. And what do I want to ask is, for example, if we have the larger image, which means we have more pixels, on the outcome we get better accuracy, as I understand.
Yeah. Not necessarily in reality. There is a problem with large images. If you have large images, basically you do not have enough memory in the GPUs to process that image. So the maximum I have seen so far are images which are 1000 by 1000 pixels. Larger images, generally, they cannot be processed with a standard algorithm. Unless you change the algorithm and you move from a classifier, a standard classifier, to a fully convolutional network. A fully convolutional network can be trained on images which are smaller, but then they can process images as you want, as large as your graphical processing unit or any processor. Generally, I mean, very well, and we will get very, very good results with images which are 400 by 400 pixels. It's not an issue at all. Did it answer your question?
Thank you.
You're welcome. Go ahead, please. The cost. Well, that Cerebras chip was just announced, so I really do not know, sorry. Just to give you an idea, the latest GPUs that you can rent on a Google provider their cost is around $20,000 per GPU. So that is probably the ballpark for something which is not custom. If it is something custom, most likely it's 10 times or 20 times as much. So that is probably the cost of a custom AI. But you can get very, very good and I would say affordable GPUs or TPUs for around $15,000 to $20,000. Any other questions? Obviously, you can run most of this stuff also on consumer grade GPUs, a maximum of 1,000 euros, and they are very, very fast in this case. Yes, please.
Can I ask one question?
Sure.
So here I cannot talk about the danger that artificial intelligence can cause to us human being. And I would like to ask one question. Can we set kind of obstacle to this artificial intelligence so that it doesn't goes beyond this obstacle and doesn't cause danger to us?
Well, I mean, think about tigers in a zoo. We are way more clever than tigers. I mean, we are not stronger than tigers, but we are way more clever than tigers. So we can basically put a tiger in a cage because we are clever. And most likely, I mean, if we will ever get to general AI, we will not be able to cage orders of magnitude more intelligent than us. So it's not a matter of putting a general AI in a cage, sort of, because it won't work, most likely. It's really around making sure that we know how to deal with something which we built ourselves, but most likely surpassed our intelligence. And we still do not know if it will ever happen. We do not know. But progress seems to indicate that eventually we will get very, very close and very, very fast. So yeah, we have to think ahead and see how to can be controlled. And I think with that we have exhausted our time. So thank you very much for your attendance and for your interest. And thank you for coming. Thank you.